The next thing we need to do with resistors is look at how we can combine them in a circuit. The reason we need to do this is that you can't just go and buy any size resistor in a shop. They only manufacture them at certain values, so we need to be able to combine them in order to produce another resistance by using a combination of smaller resistors. In class, we'll have a look in more detail at what some of those ranges are that resistors are sold in. There's some interesting things to note about them, but for what we need to do here, we need to consider connecting resistors both in series and in parallel. So we'll start with in series, and when we're talking about something being connected in series, hopefully this is just a refresher, we're talking about one being connected after the other. Another way to think of that is that there's only one path for current to flow through. And so that means it's a fairly simple scenario. And to explain this in a bit more detail, we'll look at a diagram. I think this is the most helpful way of dealing with understanding how to add resistors in series. It's fairly intuitive when you think about it, but a good way to explain it. So we're going to look at this connection where we've got a potential difference of V on the left and 0 volts on the right. So note I'm not showing the whole circuit, I'm just showing this series component of resistors. This resistor on the left will be R1 and the other one we'll call R2, and they have a current I flowing through them. We can consider how much potential difference there is across each resistor. So if we look at both of these two potential differences, we'll call this one V1, and from Ohm's law we know that's going to be equal to R1 multiplied by I, and this one will be V2, that's going to be equal to R2 multiplied by I. Now when we're combining these resistors in series, what we're really doing is trying to figure out what an equivalent resistance would be if we were to replace both of those two resistors with a single resistance. So this method of redrawing the connection can sometimes make it a little bit easier to make sense of what's happening. So we're still going to have 0 volts and V volts as the two terminals. We're still going to have the current I flowing through it. We're now going to have a resistor here that's going to be R total. And if we apply Ohm's law to that scenario, we have that V is going to be equal to R total multiplied by I. Now I've written that there so we can sort of build up to that. If we go back now to the first connection that we had, you can see there that we've got a total potential difference V, and we have two smaller potential differences V1 and V2 that have to add up to give V. So we can write down that V is equal to V1 plus V2. We've already expressed what V1 and V2 are equal to, so we'll substitute those values in. So we've got there that it's R1I plus R2I. Note that both of those terms have I in it, so we're going to factorize I out, and we're left with R1 plus R2 in the brackets. Hopefully you can see a similarity there. In both of these equations we have V and I, and we have one other term being multiplied there. So in the bottom it's R total, in the top it's R1 plus R2. So what we can say then is that R total is equal to R1 plus R2. So in series all we need to do is add those resistances together. Now if we had a third or fourth or fifth, then we just need to keep adding those. So we can represent that in this equation by just including a few extra dots there to show that we can keep adding resistors in series by just adding them together. To relate back to the factors that affect resistance, you could think of this as being extending the length of the resistor. So if we had R1 and R2 both being the same resistance, we're really just doubling the length, and so the resistance would then be added together to get the total. So it's another way to think about how to add resistors in series. The other type of connection we need to have a look at is parallel connections, and again to hopefully just refresh your memory, for parallel we're looking at the resistors being side by side. And again, if we think about current, there are now two or more paths for current to flow through. The other thing that's important to note here as well is that the potential difference will be the same across a parallel connection. So we'll again have a look at this diagram set up. So in this case we've now got two paths side by side, so that current can then split and flow through each of those paths separately. We'll then recombine on the other side to produce that same current. So again, we'll start with voltage V and 0 volts on the other terminal. We'll have R1 at the top and R2 at the bottom. The current over here is I, but that's going to split into two currents. So this one will be I1 and the one down the bottom will be I2. Again, if we look at what's going to happen for each resistance, for the top resistance, the potential difference is going to be V, so V is going to be equal to R1, I1. We're going to just rearrange that and identify what the current is going to be equal to, so that's going to be V on R1. Similarly, for the second resistance, V is going to be equal to R2, I2, and so the current there, I2, will be equal to V on R2. Again, what we're really looking for here is a situation of replacing those two resistances with a single resistance. So this will look very similar to the diagram at the bottom for series components. So we're looking for the total resistance again. The potential differences are still the same, and the current now is I. So again, the voltage is going to be equal to total multiplied by I, but we're going to rearrange that and say that I is equal to V over R total, and I'm going to make one last little adjustment to that and identify that we could write that as V outside of 1 over R total. The reason why I'm writing like that will become apparent in a second. If we go back to the diagram that we have at the top, we can see that the current's going to be split into two, but those two currents have to add to give that original current. So I is going to be equal to I1 plus I2. Again, we can make those substitutions for I1 and I2. So I1 is going to be V on R1, and I2 is going to be V on R2. Note that both of those terms have a common term of V, so we're going to factorise that out the front. So we'll be left with V outside of 1 on R1 plus 1 on R2. Now again, we have these two terms that are the same, so we've got I there and we've got V there, so what's left has to be equivalent. So we can write then that for resistors in parallel, 1 on R total is going to be equal to 1 on R1 plus 1 on R2. And again, if we had a third one in parallel, we could then just add another 1 on R3 term, and so on and so forth for more resistors. So resistors in parallel, we have that equation, 1 on R total is equal to 1 on R1 plus 1 on R2, and so on and so forth. Another way to think about adding resistors in parallel is that you're actually increasing the cross-sectional area for the current to flow through, and as we know with factors that affect resistance, if you increase the cross-sectional area, you actually decrease resistance. So there's a key point to note here, and that's that for resistors in parallel, that total resistance, it's actually going to be smaller than either of the two components, or if there's more than two, any of the components. So it's always smaller than any of those component resistances. It's a good little check to make sure that the answer that you've calculated is correct. So if you've got two resistances that you're adding together, then your answer, if they're in parallel, should always be smaller than the smallest of those two resistors. So there's just a little check that you can use when you're doing any calculations with resistors in parallel. The last point to note is that you're not always just going to have a series or a parallel connection. You might have a more complex combination, and there's no quick way of doing these. It's basically just a step-by-step scenario. So it's sort of like think of it as being in maths, that idea of doing brackets first and then multiplication and then division and so on and so forth. So you need to actually simplify each successive combination as necessary. And it's a little bit of becoming familiar with the process, and the more you do it, the more you get used to it, and the more you understand which resistors you need to consider first. To make sense of that, let me just do a quick example, or at least show you a simplification. So imagine we have a parallel connection where in one branch we have two resistors that are in series, and in the other branch we have a single resistance. So we now need to consider both a series combination and a parallel combination. So if we call this one R1, R2 and R3, the first step in simplifying this circuit would be to do the series connection. So we're going to replace those two resistors at the top with one single resistance, and we'll call that resistor Rx, just to make sure it's a very different label. So this one's Rx and the bottom one's still R3, and we would calculate the value of Rx by adding R1 and R2 because they're in series. The next step is to consider the parallel connection that we've got here, and so we're going to simplify that again and replace both of those with one single resistance, and we're going to call that one RT, so capital T for total. And because we're considering parallel resistances, we now need to consider 1 on RT being equal to 1 on Rx plus 1 on R3. So there's one simple example of how to combine resistors when you've got a more complex scenario. You do need to consider step by step which combination is going to need to be added together first before you then move on to the next step. And as I said, redrawing the circuits with these diagrams often makes it much more straightforward and easier to understand whether you follow the correct process.